AP Chemistry, and welcome to Chapter 6. So what we're going to do is we're going to quickly recap sections 6.1 through 6.3, which you were supposed to have already read and done on your own, much of which is a review from last year. This whole unit will be maybe like half review and half new, which is kind of nice because, that's better than all brand new, right? Anyway, so moving along. All right. So, wave and nature of light. So this is something we definitely talked about last year. This we looked at last year, the electromagnetic spectrum, right? Wherein, right, we know we have a wavelength and we know we have frequency and we know that they're inversely proportional based on this equation, right? Where the speed of light is a constant for the speed, right, the distance per second that all light, which includes all electromagnetic radiation, travels in a vacuum, right? And that equals the relationship between wavelength times frequency, right? Remember that when you're describing frequency, it is the number of waves in a given 1 second window, and this is the wavelength, and the standard unit for that is going to be ding 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 meters, because C is in meters per second. Okay, so and don't forget that this is commonly reported in hertz, and every time we see hertz we should think to ourselves, that actually means 1/seconds. Okay, so here again, just like last year, there's no expectation that you memorize that radio frequencies are from 10 to the negative first to 10 to the third meters. Okay, but it is expected that we know that gamma rays are the highest energy, right? X-rays come next, UV, then visible, right? Ultra, meaning just beyond, violet, right? Then we have the visible spectrum, okay? Then we have infrared, so infra, right? Just beyond or just less than red. Okay, then we have our microwaves and our radio frequency. So you should definitely know this in order of energy. That's how I like to think of it, right? Highest energy to lowest energy, right? Highest to lowest, and then we continue onward. You also need to be very comfortable with the fact that the visible spectrum makes up only this tiny, tiny window, right? This is all our eyeballs are able to perceive. Okay, and then once you memorize that this is an order of energy, right, you can deduce, right, what their relative wavelengths or frequencies are. Okay. All right. The concept of quantized energy, again, we talked about this last year. This year, a couple of things to take note of, right, is where the idea comes from, right? So historically, right, people were always aware that when things reached a certain temperature, they started to emit color, right? And that color would change based on temperature, right? As the temperature got higher and higher, right, the temperature would change. But it wouldn't happen, at low temperatures, right? It had to reach a certain temperature before it would happen. And it would have to reach another certain temperature before it would change colors, okay? Which led to the idea that perhaps energy comes in or can be absorbed in just distinct amounts, okay? And over here, the photoelectric effect, really important because we're going to talk a little bit about it more in class and in activity, right? But here, what was noticed was that if we take a metal, right, and we run an electric current, we shine a light on it, right? What happens is that we know that even though these aren't connected by any wires, right, we know that this will conduct electricity, right? Shining the right wavelength of light on here will basically close this circuit, okay? And then people wondered, well, why does that close the circuit? And especially because, again, kind of like over here, right, it had to be a certain wavelength, okay? It had to have a certain amount of energy, otherwise this did not occur, right? Which led to the idea of quantized energy, right? That energy comes in distinct amounts, or that things can absorb energy in distinct amounts, okay? Which also gives us our equation, E equals h nu, right? Where energy is equal to Planck's constant, which is, definitely memorize this, 6.626 times 10 to the negative 34th joules times seconds times frequency, okay? And technically, if we're being really specific, this is the energy of a photon, okay? Which means that if we want to talk about a mole of photons, we would calculate our energy, and then we would have to use Avogadro's number to get to that last piece, okay? All right, moving along, the line spectra, okay, or line spectra in general, give us the Bohr model of the atom. Your book did talk about this last year, but just to refresh our memories, right, we know that if we take our general kind of light and we put it through a prism, we understand that we are going to get a continuous spectrum, meaning we are going to see the entire Roy G. Biv spectrum with no blank spots, right? Nothing missing in between. It turns out, though, when we take elemental things, right? So here we have a sample of neon. Here we have a sample of hydrogen. When we take those and we excite them, right? So we run a current through them, they give off a light, okay? Just like a flashlight would. If we take that light and we focus it through a prism, instead of getting a continuous spectrum, we get individual bands of color, okay? So what that means is every other color in this spectrum is missing, right? So here we have all of these. Here we only get this few, right? Neon shows a few more colors, but again, not a continuous spectrum. So these would be referred to as line spectra, where this would be our continuous spectrum, okay? Scientists puzzled for a very long time about what this could mean, right? And this also gave birth to the Rydberg equation, which you no longer have to memorize, but it does help us to predict what these energies are going to be, right? But anyway, Rydberg equation didn't do much for us except give us the mathematical relationship here. Eventually, Niels Bohr came up with the Bohr model of the atom, where he predicted that these actually corresponded to energy levels within the atom, okay? Now, if we think back to middle school, right, we understand that we have our nucleus, right, and then we have our orbits, right, or shells, right. Do be mindful it can go by either of those names. So if you see shell model, know that that means Bohr model, okay. So we have these orbits or shells, and electrons exist on those, right, and they sort of move in a circular orbit, okay. Thinking again back to last year, what that means is that if we have a given electron here, right, what will happen is that it can absorb some energy. It will absorb a photon. So this is absorbing a photon, where a photon is what again? Right, a particle of light, right, or a particle of energy, okay? So it's going to absorb that photon, and then spontaneously and on its own, it is going to relax. And it's going to emit that same photon, okay? And that photon is going to have a wavelength. And this is going to have a wavelength and a characteristic energy. I should use a capital E, shouldn't I? And a characteristic frequency, okay? And this is what we actually see. So again, absorb photon, it relaxes and emits the photon, okay? So the electron goes back down. This photon that comes out is what we actually see. So do be mindful, that's what we're seeing. We're not actually seeing the absorption part, we're seeing the emitted part courtesy of relaxation, okay? Now, couple of notes about the Bohr model, which again we kind of talked about last year, right? It wasn't correct except for one electron species, which means not incredibly useful because the vast majority of our elements are more than one electron. Takeaway points though, right? This is still true, right? It is still true that electrons can't exist everywhere. They exist in specific places, right? And those specific places have specific quantum numbers, right, or defined energies that describe them, okay? In addition, this part is still true, right? This still describes what happens in an atom, right? Electrons absorb energy, they then spit that energy back out in the form of a photon when they relax, right? So all of this part of the Bohr model is still true. We've just refined it now, so that way it helps to better explain the rest of the atoms on our periodic table. All right. This is our introduction. Come back for the rest of Chapter 6. Thanks for listening. Be good, and I'll see you soon. Bye.